In the first question, a student is determining the mass of a meter rule by a balancing method. So what he's using a simple concept of the moment. According to the moment, the weight of the meter rule, if it is exactly uniform, then it will act at a 50 centimeter mark. So this weight will produce a moment that is anti-clockwise, and the mass which is placed, a block Q is placed, that will produce a clockwise moment. So when clockwise and anti-clockwise moments are equal or same, then we can use a conservation the law of the moment, that the force multiplied by distance, which is causing a clockwise moment, is equals to force multiplied by distance, which is causing an anti-clockwise moment. So student, he places a meter rule on the pivot, then places a block Q with a center at 95 centimeter. So it is placed at 95 centimeter mark. The students uh, stated that it is difficult to place a mass accurately at 95 centimeter mark. Like it's difficult to exactly place at 95 centimeter mark. Explain how the student could overcome this, and you may draw a diagram to help your answer. So how the student can know that he placed the mark exactly at 95 centimeter mark? So for this purpose, what student can do, he can have a width, or he can find the marks at the edges of the mass and take an average. For example, if one of the mark is 94 and the other edge the mark is 96, so how I will know where is the center? So we can just use these values and take an average. So 94 plus 96 divided by 2, what we'll get? We'll get an average that will be 95. So when the load is bigger than the when normally the load is bigger than the width of the rule, we use this technique, like we just simply measure the marking at the edges and take an average. Or what a second thing what student can do, there's another way, that like this is an object. So beginning or the start of the experiment, student mark the center of this object, and when he plays this, so because there's already a marking on the object, so using this marker he can identify that the center is at 95 centimeter mark. So there are two ways to do this. You can write any one of them. If you're looking at, like, this is a meter rule and you're looking from the top, this is the object. So to know that the center is at 95 centimeter mark, we'll measure the markings of both edges and take an average. That will give us the final answer. Or there's also another way what we can do. Before the start or the beginning of experiment, we can just mark the center of this object, or locate the center of this object, and we mark that. At the start of experiment. So both cases, the answer is correct. And when they say you may, so it's better you should draw. Maybe your explanation is not correct, so your figure will give you, the diagram will give you the mark. A student keeps the block Q at 95 centimeter and adjusted the position of a meter rule on the pivot until the rule is as near to being balanced as possible. Describe a method to find the point at which the meter rule is as near to being balanced as possible. Like what we should do, the experimental procedure, that the meter rule will be balanced. The load Q or block Q is placed at 95 centimeter mark. So for this purpose, what we should do, we should slowly move the pivot small distance to and fro. In part A, the question was how you can make sure that it is at 95 centimeter mark. The center of the load is 95 centimeter mark. So what you can do, you can read the values at the edges and take an average. Like one of the edge, the value is 94, another edge, the value is 96, and I take an average, I'll get 95. Or I can start the experiment by initially in the beginning of the experiment, I mark the center of the load, and that is I can easily locate the position when I mark the center of this load, the beginning or the start of experiment. So these are the ways to do this question 1, which is of 1 mark. Question 1 part A. Part B, student keeps the block. So he's keeping the block and adjusts the position of the meter rule on the pivot until the meter rule is as near to being balanced as possible. Describe a method to find a point at which the meter rule is near. So how a student can find like at the position where the meter rule will balance. So practically how will work out. So we will move the pivot to and fro to locate the balance point. So what we will do, this pivot is there, so we can move towards right or we can move towards left to identify the exact position where we should place this pivot so that the meter rule can be balanced. So we will find the point which just tipped one way and move the rule to find out the point which it will tip other way, and then balance point is between the point where the rule tip either way. So basically this is a complete answer. Move the pivot to and fro to locate the balance point, the point where it is balanced. Yeah, practically this experiment is difficult to do. Reason for that, it is difficult to balance a meter rule when the load is placed on it. That's a difficult thing, but this is the way experiment should be done. That first a pivot is placed here. Example, when you place a pivot and you found that because of this load it tipped towards the clockwise direction. So it means the clockwise moment is more. Now what you will do, you will move or change the position. You will change the position of the pivot to find the balance point. Like example, you place a pivot here. Then what happened? You will find that it rotate or tip anti-clockwise direction. So what you conclude that you can identify now that actually the pivot, the center point should be between these two markings. When I place at A, the clockwise moment is more. When I place at B, the anti-clockwise moment is more. So I should place a pivot between this region to and fro so that I can locate the exact point. So another way to answer this question, first you will mark a point when this meter rule, rotate or tip clockwise, and mark a point when the meter rule rotate clockwise and then move in opposite direction, and mark a point where when this meter rule rotate anti-clockwise and then find the balance point between the two markings. So this is how it is done. Like we move the pivot. That's the same thing in the first answer. I just mentioned that in short, that move the pivot to and fro and then find the balancing point. This is in detail, that move the pivot. Example, first you mentioned towards right, then it will be towards left. So marking or finding the 2 points, which one rotate clockwise, another anti-clockwise, and between these two markings, try to figure out the balancing point. Is it clear? The next part, the student determines the distance A between the center of the block and 50 centimeter mark, and also the distance B, the center of the block and the pivot, block Q and pivot. He repeat the procedure for position of a block at 90, 85, 80 and 75. His results are shown in the table. Plot a graph for A against B. You do not need to start your axis at origin. So when they say we don't have to start our axis from origin, means we don't have to mention here it start with 0. So we have to plot a graph between A and B. So when we want to plot a graph between A and B, the minimum value of A is 25 and the maximum value is 45. Minimum value for B is 20 and the maximum value is 39. So, and A is on x-axis, A is on y-axis, B is on x-axis. So what I can do, I can mark a point because I don't have to start with origin. Like we don't need 0. So I can start with a 20. Then this will be 30, 40, and the maximum value is 45. So that will be 45. Here two boxes stand for 1. That is A, which is on y-axis. What about x-axis? X-axis we have B on x-axis. The minimum value of the B is 21.4 and the maximum value is 39. So I can also start this with 20. Then this will be 30, 40 and so on. And you should label the axis like what quantity you are plotting and the unit for this quantity. So A is on y-axis and the unit is centimeter. B is also on y-axis, unit is also in centimeter. when they mention, because your graph should cover about 75%. So your graph should cover 75% of the paper. Example, because the values are too small, so even like student think I can start with 0. So I took this value as 0, then this one is 10, 20, 30, 40. And same thing when I write for this one, this will be 10, 20, 30, 40 and 50. But this part of the graph will not be used. Why this part of the graph will not be used? Because I don't have any value. The value of A and B, there is no value of A or B which is less than 20. So this part is not used here. That is why if they mention that you do not need, so it's optional, like you do not need to start your axis at the origin. The main reason for that, plotting a graph, marking the point, and using a 75% of your graph paper is having the mark. So you should use the space which is available, try to extend your scale. So these are the axes which I marked, because when I mark this point, I will have 20 and 45 here and 20 and 40. So I can use these values. When I plot my result, I'm roughly sketching a graph. 45, 39, 40, 35, 45, 39. Maybe my points might not be accurate because of the screen. So 45, 39, 40, 35, 34.3. So when we sketch a graph for this, what we'll get a straight line. And from this straight line, determine the gradient. So how you'll find a gradient? As you will solve this question, you will send your answer plot after plotting a graph. So you'll use the formula y2 minus y1 over x2 minus x1 to find the gradient of this graph. The next part, the mass r of a meter rule, mr of a meter rule, using the equation. The equation is given to you. So when equation is for paper 6, you don't have to memorize any formula. Example, I'm taking a value of a gradient, say this was 10. Example, it can be any number, I'm just taking 10. So you have to use this formula, mr, the mass of the meter rule, is equals to m divided by g minus 1. So that is 20 divided by g is 10 minus 1. So that will be equal to 20 divided by 9. You will get the answer for the meter rule. But this is not the right answer. It's just I took a value of gradient as 10. According to your gradient, you will write the answer here. Another thing, two students carry out the experiment correctly, but with different values of the mass of Q. One student obtained the value of a B larger than those obtained by other student. State and explain whether the larger value of a B likely to produce more accurate result value of mass of a meter rule. Basically, when you are measuring a large value, the larger value reduce the percentage error. How the larger value reduce the percentage error? Because the formula for percentage error is the smallest value which instrument can record divided by value recorded multiplied by 100. That is the formula for percentage error in the measurement. So smallest value which the instrument can record That is because when we are using a meter rule, what is the smallest value which a meter rule can record? That is 0.1 centimeter. The smallest value which it can record is zero point 0.1 centimeter. Divide by value recorded. So example, two students perform the experiment. One of the student use the value of a b, example 20. Another student uses the value of the b 30. Which one is having a less percentage error? So how to find a percentage error? Smallest value which the instrument can record divided by value recorded, which is 20 multiplied by 100. And for another student who used the same apparatus but recorded the larger value, like 30 multiplied by zero point 0.1 divided by 30 multiplied by 100. What is the answer here? Zero point 0.1 divided by 20 into 100. 0.1 divided by 20 multiplied by 100. So 0.5% error. And what about the other one? 0.1 divided by 30 into 100. 0.33% error. So you can clearly see the student, though both students perform the same experiment, but the student who is recording a larger value is having a small percentage error. So in the question, the same thing they ask, state and explain whether a larger value of a B are likely to produce more accurate value for the mass of the meter rule. So you will say yes, and reason is that when we record a larger value, we'll have a smaller. The larger value which we record has a lower percentage error, so experiment will be accurate. So whenever you are performing an experiment, you prefer to record larger values, greater numbers, so that the percentage error in your experiment will be reduced. In the next question, some students are investigating how the volume of the water affects the rate at which the water in beaker cools. They are using the apparatus shown in figure 2.1. 200 cm cube of hot water is poured into a beaker A. Initial temperature rises to a value shown on thermometer A. In a first row of table 2.1, record the temperature at time is equals to 0. What is the temperature value here?
87.
So 87, and that you have to record in table. So that is equals to 87. Then what about the initial temperature in beaker B? Temperature of the water in beaker B?
89.
89. So that's 89. The temperature theta A and theta B of the water in each experiment at time 30, 60, 90, 120, 150 and 80 are shown in the table. Complete the headings and the time column. So complete the column heading and you can use the screen annotation to complete this. The column heading means the unit and the value for the time. So 0 is there, the starting of experiment, then 30, 60, 90, 120, 150, and then the last one is 180. So this was 30 and this was 90. So after 30-second interval, student is recording, and the column heading, the unit of time is second, temperature is Celsius, degree centigrade. Describe one precaution which should be taken to ensure that the temperature reading in the experiment are accurate as possible. Like student is doing this experiment, how he can make sure that his temperature readings are accurate as possible. So he should look perpendicular, avoid a parallax error. That is one thing. And yeah, look perpendicular, avoid a parallax error. That's one. And there's also another thing, because when we are recording a temperature at the beginning of experiment, to ensure that his temperature reading is accurate as possible, as he took a hot water and he immersed or put this thermometer inside, so the temperature reading will continuously change. So students should wait until the reading on the temperature scale or stop rising, or thermometer should not touch the bottom of a beaker. That's also there. So look perpendicular, avoid a parallax error. That's one thing. Or wait for temperature to rise to maximum value. So before starting the stopwatch, he should be make sure that the temperature value rises to maximum value, and then he will record that. Yeah, equal for liquids, it should be stir as well, so that uniform temperature throughout the mixture. The next part, write a conclusion, start stating how the volume of the water in a beaker affects the rate of cooling of water. Justify your answer by reference to the result. So in the first one, we took 200 cm cube, and the second experiment we took 100 cm cube. So in the B, this is 200 and 100. The starting temperature, this was 87, and the starting temperature is 89. What is the difference in the temperature in 3 minutes for beaker A? That's 87 minus 77.5. So 9.5. And what is the difference in the temperature? 89 and 74.5. That's 14.5. So means for beaker B, the temperature change, the change in temperature is higher and its volume is less. And for beaker A, its temperature change is smaller, but its volume is higher. So what we can conclude, how we can say or write a conclusion for this, we can say that the rate of the cooling is inversely proportional to the volume, like, or the temperature change is inversely proportional to volume. The one which is having a larger volume, sorry, the rate, yeah, as the volume is increases, the rate of the cooling is decreasing. This is about the rate of the cooling, because larger volume cool down slowly, smaller volume cool down quickly. And they mentioned with reference to the result, so you have to use the number, like you will say a 200 cm cube a beaker A with a 200 cm cube of water shows a temperature change of 9.5. A beaker B with a 100 cm cube of water, temperature change is 14.5. So you have to write this in your result. Because justify your answer by reference to the result, so you have to use a number. Like one is for statement and another one is using a result. Like for A, the temperature change was 9.5 when you took 200 cm cube. For B, the temperature change is 14.5 when you took 100 cm cube. The next part, using the results of 100 cm cube of water, calculate the average rate of cooling for first 90 seconds. For first 90 seconds, theta not means the temperature at when the beginning of experiment, and theta 90 means temperature when after 90 seconds, and divide by the time interval, that's 90. This is 30, 60 and 90. So beginning of experiment, it was 89. At 90 second, it was 80.5 divided by time interval 90. So what's the answer for this? 89 minus 80.5 divided by 90. 0.094 centimeter cube, the temperature change degree centigrade per second. And what about the second one? The temperature change from using a results of 100 centimeter cube of water, calculate the rate of cooling for last 90 seconds. So for last 90 seconds started with 80.5 and ending at 74. So 80.5 minus 74.5 divided by 19. What's the answer for this rate of cooling? 0.067 degree centigrade per second. The temperature change divided by the time interval. So in the question they ask, a student suggested that it is important that the experiment with two volume of a water have the same starting temperature. State whether your values of x1 and x2 support this suggestion and justify your statement with your result. So when we are comparing this, as a student suggested that it is important that the experiment with two volumes should have the same starting temperature. State whether your values of x1 and x2, the value for x1, the rate of cooling in the first 90 seconds was 0.094 and x2 was 0.067. So does it support the theory? As you can see, when the temperature changes are different, the correct answer, the statement is true, yes. Because what happened, you can clearly see from the result that, for example, when it started with 89, in 90 seconds it cooled down to 80.5. But when it started with 80.5 in 90 seconds, it cooled down with a smaller rate. So basically the initial temperature affect the rate of the cooling, And that is also a suggestion here in the question, as a student suggested that it is important that the two volume of the water should have a same starting temperature. Otherwise, if they have a different starting temperature, then they might have a different rate of cooling, because the temperature of the water also affect the rate of the cooling. So justification here, the statement is yes. And justification, you can justify with value of x1, like x1, the rate of the cooling was 0.094, and x2, the rate of the cooling is 0.067. When the this is when the starting temperature, when it start at 89, this was the rate of cooling, and when it start at 80.5, the rate of cooling is different. So student statement is true, that the temperature or the initial temperature of the water affects the rate of cooling. Another student planned to investigate whether more thermal energy lost from water, uh, from the water surface than from the side of the beaker. Describe an experiment that could be done to investigate. You may draw a diagram. So similar experiment, the student want to make sure that or identify that the rate of the cooling is affected by, or it occur at the surface, larger surface, greater rate of cooling. As another student plan an investigation whether more energy is lost from water surface than from the side of the beaker. So how he can work out this? First one, he will insulate the beaker. He will insulate the beaker and there is no lid. That is one. And the second one, you will do with a beaker which is having a lid but no insulation. And then use the water, same amount of water. You will use the same amount of water and same starting temperature. Then compare the temperature changes. Is it clear, this part? So this is the second question from paper 6. I'll share another link.